In this video, we are going to derive two equations of motion under the assumption of constant acceleration. So the first equation that we are going to derive is to go from acceleration to an equation for velocity. So from the left, acceleration is the time derivative of velocity. We're going to go to the equation on the right-hand side of the green arrow, where we get velocity as a function of time with the initial velocity and the acceleration. So how do we do this? We start off by saying that we have defined acceleration to be dv dt, your instantaneous acceleration. So if we multiply through with dt, we get dv is equal to a dt. Now we integrate on both sides of the equation, and we integrate from our initial velocity to our final velocity. Dv is therefore equal to a, the integral of time from 0 to t. Now, because we assume that acceleration is constant, we can take the a out of the integral sign. You will see that we'll do a problem in the end where acceleration is not constant. Then you need to keep that in mind and integrate the a. We'll do an example like that. But so if you assume acceleration to be constant, you can take it out of the integral sign. You get a integral from 0 to t dt. Straightforward integration, and we substitute in the boundary values, and we get v0, which is your initial velocity, minus v is equal to at. And we take v0 over to the other side, and then we get v, our velocity, is equal to v0 plus at. Now if you think of this intuitively, it makes sense. If you have a particle moving at a certain initial velocity, v0, and you apply a constant acceleration, then the end velocity after a period of time would be the initial velocity plus the constant acceleration multiplied by the time. That makes sense. If you apply that acceleration for a longer period of time, then the final velocity is going to be larger. Okay, so it's a linear increase in velocity. And you can also see that the units work out. So v is the unit meter per second, a is meter per second squared, and t is seconds. So a times t gives you meters per second squared times seconds. So that gives you meters per second. So the units are consistent in this equation. V is equal to v0 plus at. We can do this under constant acceleration. If the acceleration changes with time, then this equation is not valid, and you'll have to go from first principles. As I said, we'll look at an example like that. The second equation that we want to derive is to go from v is equal to ds dt to an equation for position. So the equation for position that we will derive is to say the final position, s, is s0, your initial position, plus v0t, plus half acceleration multiplied by time squared. Once again, it's under the assumption of constant acceleration. So how do we do this? We say we know that the velocity is ds dt, that's our instantaneous velocity. And so we multiply through with dt, and we get ds is v dt. Now from our previous equation of motion, we know that v is equal to v0 plus at. So if we substitute that into v, we get that ds is v0 plus at dt. Now we integrate both sides. On the left hand side, you integrate from s0 to s, and on the right hand side, you integrate over a certain time period. So that is from 0 to t. On the left hand side, you'll get, after integrating, s minus s0. So in this line, I've just taken the s0 over to the other side already. And if you integrate on the right hand side, it's basically two integrals that you do. You integrate v0, so you get v0t, and then plus we need to integrate at. A is constant, comes out of the integral sign, and the integral of t would be 1/2 t squared, and between 0 and t. So that gives us an equation for position when acceleration is constant of s is s0 plus v0t plus 1/2 at squared. So how do we apply these equations? Let's look at an example where we can use these.